two things, I guess. There's an exponential growth thing that we're going to look at, and the other thing is looking at what happens to base parent graphs. So if I have something like this, we've done stuff like this already. This right here would control your vertical, could be a stretch or a shrink. This over here, the H and the K is left and right movement. This one is going to be counterintuitive because it's going to be opposite. Well, sorry, this should be minus H and plus K. When we do these out, this is always the opposite of what you would think it is. So this is left or right. And remember, it's the opposite of whatever the sign is. And over here, this K value, this is going to be, for the K, this is going to control your up and down. Now, we'll get into more manipulations on what this will give you when we look at exponentials, but understanding that if you're adjusting what's getting done to the input value, this is the argument of the function. So if you adjust the argument, that's going to shift it to the left or right. In most cases, sometimes there's a negative effect when you factor it out. If there's something getting done to the argument, you move left or right. If there's some movement after the function, that controls the vertical up and down translation, whereas this would be a stretch or a compression. But it's not a dilation, because with the dilation, the x's change. This is literally just pulling it up or shrinking it down. So the first step should be kind of easy. We've got to graph 3 of the x. You'll plug that in a minute, but without graphing it, what would your domain on this one be? If you were to graph out 3 to the x, what would your domain be? What do we think? Yeah, so you can just say. What? Yeah, your domain is going to be all real numbers, because every input's going to give you an output. Now, think about those outputs, though, that you would get. And we looked at making a table of them the other day. What would the range on this graph be? Yeah.
0 to positive 10.
Yeah, because it's impossible for us to get out some negative value. Because even when you plug in a negative exponent, like what's 3 to the negative third going to equal? I plug in I'm trying to get a negative output. What's 3 to the negative third going to give me? 1 over what? Yeah, it would give me 1 over 27. So, and what would our y-intercept on this be? That means you plug in an x value of 0. What would your y-intercept on this graph of 3 to the x end up being? 1, yeah. So you can give a reasonable graph. I mean, we can go through and you can plot it out. But remember, it's going to go through 1, 0. When the input's 1, you've got 3, 2 would give you 9. And then you've got 1/3, 1/9, and so on. So go into your calculator and plug that first one in.
Oh, I lost me.
Sorry. It was saying that there's a connection error. So go in and do 3 to the x power, and this is what your graph is going to look like. That's the same as what we said it was going to look like before. We can grab a screenshot of it so we have something to go through in reference. So you've got something like this. This is what 3 raised to the x power would look like. This is going to be what we're going to base all of our subsequent equations on. And notice, one of the things that's bad about this calculator is that it really screws up the scaling on this graph. Looking at what we've got, see how this isn't as long, so you almost need to take it and make it longer to make it be an actual 10 by 10 window. But in any case, that's what your graph should look like. What's going to happen? What do you think is going to happen before we plug it in question A? What do you think that graph is going to look like compared to the parent function? Tyler?
It's going to shift it right.
So we think that this means that we're going to shift this graph to the right 3. So looking at that, go into your calculator and see if he's right. So there's your base parent graph. We're going to do x minus 3 as the exponent. What does that do? There you go. Shifts it over to the right 3. So your graph, I guess, would look more like this. as opposed to that original parent graph. Um, All right, so the next one's going to look like this. What do we think this would look like if we took this graph? What transformation do you think would be done on it? What shift would be done on this parent graph to get your new graph here? Yeah, this would mean that we're going to go over to the left 4, go into your calculator and confirm or dispute what we got. So you can go back, you can change what F2 is instead of having to re-input everything. And then it would be, we said x plus 4 is the power. So there you go. So it slides it over to the right-hand side. Take this over. Something like that. What about negating the x? What do you think would happen if you negate the x? Think about a point that would be on the graph, like let's say 1, 3, right? Now, when you negate the x, you would have, so if my input's 1, it would be technically, and if I plug in a 1, the function's going to negate that, so I'd evaluate out 3 to the negative first. What do you think that that's going to cause if you negate the input? It's going to be a reflection, perfect. What kind of reflection do you think you'd have?
Reflection over the y-axis.
Let's double check, but I bet you're right. Let's see. Did that work out? It should be a yes. Next one up. We got to go over to the other page. What do you think happens in D? We can go through and just start listing out what these transformations will do. What do you think is going to happen in D? What transformation will we do? What's that? Yeah, this is going to end up being shifted down 3. So you take the original parent graph. So this one would look something like this. That's probably not, well, maybe-ish. We could do a little bit better. But what do you think the E is going to have done to it? Yeah, that's going to shift it up 4. So this one was down. Oh. This one over here would be down 3. This one over here is going to be up 4. So the graph would look like it did before, except it would be higher. And the asymptote line that normally is going to be the x-axis would now be the line y is equal to 4. So it goes from y equals 0, y equals 4. This next one is interesting too, because most people are going to screw this up. The base is not negative. It's the negative of 3 to the x power. What do you think is going to happen if I take 3 to the x and then negate it? What type of transformation would I go through and have? Yeah.
Reflect over the y-axis.
There you go. This would be a y-axis reflection. So if you do that graph, it would look something like this. Because remember, this is the same as graphing out the negative of 3 to the x power. Those are equivalent to each other. It's the negation of 3 to the x. Order of operations tells you handle the exponent before any multipliers in front. What do you think this graph would go through and have for G? What do you think G would go through and have done on it? Yeah, it's going to rise and technically decrease twice as fast. So this would have, so this graph would sort of ride along here and then shoot up like that really, really fast. And then the next one for H, this would be a vertical compression. So the y values in this case would be half of what they were before. So it's going to take it a lot longer to go through and rise up. Whereas the other one shot up very quickly. This one's going to be delayed. Now this next one's going to be more interesting because you've got two transformations going on here. What does the negative cause to happen when it's in front like that? What did we say the negative cause to happen? What? Over what? Okay, so we're going to say that this has an x-axis reflection. And then it's also going to have something else done to it, which is that 1.5 in front. And that would give you a... So this graph is exclusively in quads 3 and 4, and it's going to be falling really, really fast when it starts falling. It's going to drop to negative infinity very, very quickly. Okay? So when we do this, here's another way of looking at it. In this case, we said that the A is a vertical stretch or compression, which means it only impacts the y value. In this case, the B would be our base of our exponential. The H is going to be our lateral movement. And the K is our vertical shift. So for the next one, if we were going to go through and translate this graph to the right 5 units, and down 7, what would the equation of the new graph be? I need to take this graph and shift it to the right 5 units and down 7. What would that end up being? Yeah.
3 times 4 to the x minus 5 power minus 7.
Go into your calcs and let's see if we can get this to work. Go in and let's see if we can make this happen. So go in and plug in, and we can get those other two off up there. 3 to the, do that, actually change it and do 3 times 4 to the x first, and then do the translated graph. So make sure that your graph window there shows both of them. Careful, what was this one? Wasn't it 3 times 4 to the x or something like that?
Yeah.
Okay.
Oh.
So go back and change that to 3 to the 4x. So now that's our first graph, and you see how even that one rises really quickly. Now this graph, I'm going to shift it, and we said we had 2 shifts. What were they, to the right 5 or something?
Yeah.
To the right 5, and then down 7. So think about taking this graph and taking all of these individual points to the right 5 units and then down 7, and that's where you're going to find the new points, to the right and then down 7, and so on. And by the way, what would the new vertical asymptote of the horizontal asymptote of that pink equation be? What would the horizontal asymptote on that pink equation be? Close. Let's be y is equal to... No. Sorry. So, does that handle that one? Graph of this axis is reflected over the y-axis and shifted up 4 units. What is the equation? How do I make it reflect over the y-axis? Do you remember? Go back and check to see those equations before, because we found one that's going to reflect over the y. You know what it be? What do you have to do to make it happen?
Having all the negatives in the base.
We'll say a negative a value, and then shift it up to the 4 units would be plus 4. What were you going to say?
Wouldn't it be a negation to the exponent?
Let's find out. So you think it's a negation to the exponent. Go in. Let's try both. Go in right now. Take that graph. plug in the original one, which was, what did we say it was? 1/2 times, oh, sorry. Go in and type in 2 times 0.5 to the x, and let's see, because that's the thing that's great. You can always check to see whether or not this is actually correct if you have the calculator with you. Do the original one, so don't do the negation just yet.
Sorry,
Oh, the original was negative?
no, it's already on the graph.
Oh, sorry. And then the second one would be to the 0.5 to the x, and then was it plus something? Yeah, plus 4. So let's look at what we were trying to cause happen. Now, we were trying to negate it over which axis? The y or the x? We were trying to do over the y. Did this cause it to go over the y? Take a look. How does this graph compare to this one? Did we reflect over the y-axis? What did we reflect over? The x. So what can we go in and change? What was our other option? Keep the 2 in front as positive, and now let's negate our input. Or technically, well, yeah, we'll say it is negative x. We'll negate the argument. So did that cause the y-axis reflection that we were looking to have? And it would be yes. So our equation on this would end up being y is equal to 2 times 0.5 raised to the negative x power, and then plus 4. So if we're trying to go through and shift this out, we're not going to negate the a, but we're going to negate my input. Okay? What transformations do we have to go through and do to get this graph from this one? There's 2 of them, and we always work sort of, we'll think of it in terms of an order of operations, but handle the outside, or sorry, the inside going out. What would be the first transformation that we went through and did? Yep, we're going to have to go over to the left 6. Now, based on how we answered the last one, what does that negation cause to happen in front? There you go. Now, the next thing we're going to work with, and this is the only other thing we're working on today, and this one actually is huge for what they've been asking. Like the number of questions that they've asked is very, very, very high as compared to what it used to be. We're talking about at least 2 to 4 questions on each of the exams. There's been 2 and 4 so far on just growth and decay. So exponential growth, the equation that we're working with is y is equal to sum a times the quantity 1 plus r raised to the t power. A is the initial amount. The r is the rate as a decimal. And t is going to be time. Now, if that's growth, what do you think decay would look like? It's a really similar formula, but how would it look different if it decayed? Yeah, the other end of it is for decay, it's going to be the exact same formula except 1 minus the rate. Now, and it should sort of make sense to you, because if you go through and let's do this. Go to your computational screen. If you went through and did something out, like let's say you go and you buy, there's a Coke, right? And it's $88. And you have a coupon for 20% off. You don't need to compute out what the 20% is to determine the final cost. You would need to go through, if your coupon is for 20% off, how much of the original amount, what percentage are you paying? 80%. So you could go in and type this in 88 times 0.8, because that's going to give you the new total of the amount. And it should make sense. Is it less or more than the original amount? It should be less by 20%. What if we went through and said, all right, this Coke now that's $88 isn't on sale. Well, even, let's say it is. 20% off, but now we have to add tax to that. And tax is, I think, 8%. So we need to add 8% to the amount. So you don't need to compute out 8% of that. You need to figure out what 1.08 of that would be so you can get the final amount. So go in and take that amount times 1.08. No, well, if you do the 0.8, that's only going to give you what the increase is. The final amount would be times 1.0, because you're always, if you multiply by 1, you're preserving the original amount. So changing, adding, and subtracting the rate off is going to give you what the final answer is modified out. So this would be a final cost then of $76.03. So that should sort of make sense for us. Let's take a look at these questions as we go through and do them. 1995, the daily cost of patient care at community hospitals has increased about 4% a year. In 1995, such hospitals cost for an average of that amount per day. Write a model to go through and do that. Well, it's increasing at a percent per year. So this indicates to me, is this exponential growth or decay? What would we have? What is it?
Growth.
Growth, yeah. So I recognize right away that this is exponential growth. Now, it's important to understand, you've got to answer the questions that are asked. First one up, write an equation to model the cost of the hospital care. Now, normally our growth model is going to be y equals a. In this case, since it's growth, it would look like this. But we can fill in a bunch of stuff. We start off and say, well, the end amount is the y. We don't know that. And nor would we in the model, because it's supposed to be, you're graphing out essentially a function. We've got 968 is the starting amount. It goes up by 4% a year. Now, something on there is intentionally wrong. What's on there that's wrong, Tyler?
It's 0.4, it should be 0.04.
There you go, 0.04. Everybody always makes that mistake as they transition. So that would be one equation, or the simplified form is 968, 1.04 raised to the t power. That final one here would be the one that you would really be expected to go through and give. Now, for the second part of it, you've got to use the equation to estimate the cost in 2010. So how could you go through and figure out what that's going to be in 2010?
You start by subtracting 1995 from 2010.
So, if you got 2010 minus 1995, how many years is that? Let's go in just so we see it. 2010 minus 1995 is going to give me 15 years. So let's go over to our function now and plug that 15 in. So y is equal, we're going to use the model for this case. Now, it's going to be an approximate cost, so go into your calculators. You type it in exactly as it looks. Part of this that's interesting is they're not going to tell you something. They're going to imply that you go through and know it. Looking at what we've got, we plug this in. Oh, you don't need to do the dynamic because there's no variable affixed in it. So press enter from there. Now, your answer is there, but you have to do some interpreting. What would that cost then be if it increased 4% a year? What would the answer to this question be? What do we think? It's not going to tell you.
$1,742.32.
Close. And it was, I'm sorry, 1,000, what was it, 743? And how much change?
32.
No?
31.
31 cents, yeah. They're not going to tell you to go through and round to 2 places after the decimal with money. So if it doesn't say so, make sure you go all the way out to that amount, to 2 spots after the decimal. Does that make sense or no? Okay. Next one up, suppose that your parents deposited that amount in, paying that amount of interest compounded once a year. So every year you're getting 3% interest. Find the account balance after 18 years. Now, one of the things that's a way, and if you have money, people that have a lot of money, like a trust or something like that, or an annuity, what it ends up doing is they take an amount, and people like somebody like Bill Gates, right? he never even has to touch his initial amount of money if he were to put it all in the bank. He would literally be able to go through and take his money and just live off of the interest alone. Because every time that you go through and if you have a ton of money, let's say you've got $100 million in the bank, you make 3.5% interest. Every year you're making $3.5 million. So it's possible to live off of that and never touch the principal. That's why some people like that would never have to go through and work. So this you've got to keep in mind is it's going to accrue money every year, and whatever they don't spend, like if you have $100 million, you make $3.5 million in interest, but you only spend $2 million. So after the first year, how much money would you have left in your bank account? $101.5 million, and then you're earning 3.5% interest on the new bigger amount. And if you didn't touch the money at all, you'd have $100 million and earn interest on 3.5 interest on that. Then after the first year, you'd have $103.5 million, and then you're earning interest on that. So you actually get interest on the interest you earned previously. So that's what compounded means. If you don't touch it, it starts growing really quickly. It's an exponential function. So we're going to start off, this is a growth model. Y is equal to A times 1 plus R raised to the T power. So in our case, the A is the initial amount, and how much was it? 1,500? 1500. Now, our growth rate is 1 plus 0.035 raised to the, in this case, 18 power. And it's important to note that these numbers should be matching. If it's compounded annually and it's done every year, as long as those are speaking the same language, you're good. You can use this formula. What do we end up getting is the amount in the account after 18 years. So we would have, without touching any of the money, 2,000. How much was it? 2,700 and what?
86. 23.
So it would be that amount in there. So that's a significant amount of money. How much money did they go through and make? Well, you would take the end amount minus the initial amount, and all of that is interest. They didn't have to work it all to make that happen. Here's another one, I guess, and I don't know how much they're going to ask about this, but this does come up. So, do you all, well, you probably are too young, but what grade do you all take chemistry in? Is it like 10 or 11? 10th grade? Okay, okay. This is something that comes up. Have you heard of carbon dating before? Like that's how the half-lives, what happens is over time, atoms decay at a certain rate. Okay, so like if there's 100 grams of a substance and you come back 1,000 years later, there might be 50 grams of it, but it decays at a known rate. So it breaks down. What they do is they'll go and find like a bone of a dinosaur or something, and they'll go through and say, all right, normally there'd be this much carbon in it, now we've got this much carbon in it, it's this old. And they can do it now with isotopes really, really accurately. Here's a really, really, really basic equation for what that is. So here's a formula that you need to know for exponential decay. It's going to be your final amount A is equal to A sub 0, which is the initial amount, times 1/2 to the T over H power. So for all of these, the equation is going to be different. You're going to have some initial amount times half raised to the T over H power. So like we'll say, all right, the half-life is 5 days. What would it be 25 days later? So that would be 25 over 5. So you always look at the half-life and then how long you're trying to take the measurement for. In this case, radioactive substance, it's got a half-life, same thing that we just discussed. To treat some form of cancer, they use radioactive iodine. The half-life of it is 8 days. A patient receives 12, whatever those units are. How much is left in the patient after 16 days? So this would be something, and this is actually a real thing. Did any of you have a relative before that has had cancer or chemotherapy? Yeah. There's a certain amount of time that you're actually, they were given the instructions you can't be near somebody for a certain amount of time? Yeah. I have a friend right now, even my sister is going through thyroid cancer. And so when you go through, she has to get some treatment, but she's actually delaying it until after Christmas because she'll get the treatment and then she can't be near anybody for like 2 weeks because she's going to be, I guess, glowing with radioactivity. We would go through to figure out the end amount. That's our A. Our initial amount was what, 12? Is that right? 12 units. And then 1/2 times, in this case, the time, which is 16 days over 8, which is the half-life. All right, so you go into your calculators, and we can evaluate this out. So what amount would we go through and have in there? There you go. So the end amount that you would get is 3, and maybe we'll put units on it. So our end amount A is equal to 3 MCI, whatever that is. Couple more. This amount is invested 15%, or it has a 15% loss each year. That's a terrible investment. You go through. This is different than the ones we've done before because this is going to be a decay. One of the things too that's very interesting to look at, like think about in terms of real world, in terms of a house. Is that going to be over time? Do houses grow in value or depreciate in value? Which one? What's that? You say that they get less? Usually? See, I'd say houses in general historically go up in value because people are always going to need houses. Normally people put a little bit of effort into keeping them up. If you let it sit there and did nothing, then it probably would be worth a little bit less. But over the course of time, houses tend to grow in value, okay? Especially the ones on the lake, because they're always, like in Webster, you know how every field, they always put, like after a while, they'll put some houses in it? That's because there's an abundance of land. You look, they're not making any more lake, okay? So like the houses on the lake are going to go up because more people want to live there, and the amount's going to increase exponentially. Very, very slow, not so huge, like 3 to the F, but it's going to increase exponentially. What happens to the value of something like a car over time? Is that going to be appreciation or depreciation? Depreciation. Just the act of owning a vehicle, like not having it be from the dealer. They always say when you drive it off the lot, it loses 30% of the value. It's actually the fact that someone's owned it. If it's not like has a clean title, meaning no one's ever owned it before, a pure title, you go through and say, all right, well, then it's worth the original amount. But if it's even had one owner, never been driven, just one owner, depreciates the value, and it depreciates right away. Like you're talking about, if you buy a new car, they're terrible investments because they lose 30% of their value just by owning. So if you've got a $20,000 car, it loses 30% of the value. It's down to 14 grand just from you owning it. This one, it's going to decrease 15% a year. So what we're going to do is model it with decay. So this, in this case, here's our general decay equation, 1 minus the rate to the t power. Now in this case, we're going to take, that's our final amount, that's what the y is. We'll take 10,500, and this would be 1 minus 0.15, and it's going to lose that amount every year. Notice our units need to go through and match up, and that's going to be something that on a test you might get wrong. Those units always need to match up. So if it's lost per year, then make sure your units are per year, the time that you're working with. This, by the way, is the same as evaluating out y is equal to that initial amount, 10,500, times, now, this would be the same as 0.85 because you're keeping 85% of it. What would the value of that investment end up being? And go through, and it would be 286115. 2861. Is this amount right?
Yeah.
Okay. So, is that a good thing to lose that amount or not? No. You don't want to lose money when you invest it. Two. These are Regents' questions. Which one would represent decay? That means that over time, it's going to go through and get less in value. Let's see if we can do it out algebraically first. And then we'll look at the graphs of this. Taking a look at what's here, look at your base. Is that going to be growing or getting smaller as we move out to the right? I'd say it's going to grow. Because my base is 2, even to the 0.3 power, it's 2, it's going to not grow super fast, but it's still going to grow. Look at over here. Is 2 growth or decay? Look at the base. Which one would you say? What do you say? Yeah, this one's going to grow as well. The base will go over y. Base is going to be 1.2. Now this one I see, I want to change something about 3. 3 and 4 need some changing in order for me to see whether it's growth or decay. What's wrong or what's awkward about number 3 or something we want to change? How?
There's a negative exponent.
So what do we have to do to the base if the exponent's negative?
If the reciprocal,
So now my base is 2 and the exponent is positive t. Would that be growth or decay? Which one? Yeah, this would give me growth. And then we encounter the same problem over here. Except what's the new base going to be in number 4? 1 over 5 raised to the t power. One of these is not like the other, and this is it. This is the one that's going to be decay. Do you know how you can tell what decay is going to be versus growth? Look at the base. What do you notice about the base and a decay versus a base and a growth? If your base is between 0 and 1, it's going to be decay because you're losing amount over time. If it is greater than 1, it's going to be growth. You could go in and plug in, let's say go in and plug in 3 and 4. Go into your grapher and plug in 3 and 4 and watch the difference with them over time. So that gives me 2 to the x power, and then the other one is going to be 1/5. Oh, careful. 1/5 to the x. See how that's decay? Like over time, this is getting really, really close to 0. This is unbounded. It's going to go on forever. So that's why that's going to be decay. Take a look at the last one. Go through and answer this one right now. This was, this is a little bit more interesting, sorry. We actually know, you do have enough information to solve this. Go in, plug this in, and let's see what it would look like. Think about your exponential growth equation, and think about plugging into that to get out something. So you tell me, boys, what would we get when we just did our plug-in? I don't need you to solve yet. What would the plug-in look like? What would we write out? Do you have it now?
Yeah.
What'd you plug in?
135,000 equals 100,000 times 1 minus r.
So we don't know what the rate is, but he's absolutely right. So far, all of that's good. This is going to be a power equation. What do we need to do in order to solve for the rate? What would my first step be? Yeah.
divide both sides by 100,000.
So go through, I'm going to divide both sides by 100,000. Now my spacing, did I give you more space in your paper?
Yeah.
Okay. Minus r, sorry, plus r. Where did I minus r? Should be plus r, sorry, to the 5th power. Now, I've isolated the base exponent pair. What do I need to do now in order to get that r value alone? You know?
Yeah. Multiply the inverse of it.
Multiply or raise both sides to the reciprocal power, yeah. So I'm going to take, now you actually could take the 5th root of both sides. That's what the 1/5 power is the same as. I'm going to raise both sides to the 1/5 power. So this would leave me with, and I'm going to list, well, I think I can do this, 1 plus r. Now, when we do this out, go over to your calculator, please, and type in 1.5 0.35, or whatever that fraction ended up being. Now, raise that to the 1/5 power, and here's what I want you to do. Now, this is a substantial amount, so this should be okay. When we do this, go in, please, and make sure you list out all of these. And I know it seems nitpicky, but especially when you get into really, really precise measurements, which we're going to be working with later, they're called logarithms. But some measures we need to be really, really precise on. So we get this amount here, this decimal, right? And I make sure that when I list it out, I put that, I'm going to, because I'm not saying it's equal to, understand that that value continues on, right? What would you do now from here in order to solve for the R? Subtract a 1, so that would leave you with 0.06185875879-ish is going to be equal to the R value. And I do the equals. Now we need this to the nearest percent. So what do we have to do to convert that decimal into a percent? Yeah, move the decimal over 2 places or multiply it by 100. What would this be? What would you give as your final answer? So the nearest percent would be 6%. Okay? Was that tough? All right. No homework. What time do we finish? We got 10 minutes. You can sit and sit.